Have you ever looked at a circuit diagram and it just looks like a total mess, like a plate of spaghetti, and your brain just kind of wants to shut down? Yeah, you're not alone. Today, we're going to build a powerful toolbox, a set of techniques that will let you untangle any linear circuit, no matter how complex, with total confidence. Let's jump right in. So here's the game plan. First, we'll talk about why our good old basic tools sometimes just don't cut it. Then, we're adding two heavy hitters to our arsenal, the node voltage and mesh current methods. After that, I'm going to show you an absolute game-changing simplification trick. And finally, we'll step back and admire our brand new, fully stocked analysis toolbox. Okay, so let's start by hitting a wall. You know, the simple rules we all learn at the beginning. They're fantastic for the easy stuff. But when circuits start to get messy, those rules can leave you completely stranded. We all started right here, didn't we? Resistors in series, just add them up. In parallel, you use that reciprocal formula. Simple stuff until, well, it's not. And then you run into something like this. Seriously, take a look. Can you find any resistors that are purely in series or purely in parallel? If you're scratching your head, you've just slammed right into that wall I was talking about. Our basic rules have totally failed us here. So, what do we do? Well, the answer isn't to just memorize more and more random formulas. The secret is having a system, a methodical, step-by-step approach that guides you straight to the answer every single time. And that's exactly what we're going to build today. First up, let's talk about the node voltage method. Think of this as looking at the circuit from a different perspective. It's all about finding the key pressure points, or voltages, in your circuit and working from there. It's really just a three-step dance. First, you pick a spot to be your ground, your 0-volt reference point. Easy enough. Then, you label the voltages at all the other important connection points, the nodes, relative to that ground. And finally, you use Kirchhoff's current law at each of those nodes to write out a few equations. A little bit of algebra later, boom, you've cracked it. Now for a really cool trick you can use with this method, the supernode. If you've got a voltage source that's just sitting between two of your main nodes, you can kind of draw a circle around them and treat them as one big single point. It's an awesome shortcut. And why is that such a big deal? Because it means you have fewer equations to write and solve. It simplifies the math. I mean, less work for the same correct answer. What's not to love about that? Okay, next tool for our toolbox, mesh current analysis. If the node voltage method was about pressure points, this one is all about following the flow. So here's the big idea. Instead of thinking about voltages, we're going to imagine these little currents that just circulate around in closed loops, kind of like they're running laps inside each window pane of our circuit diagram. It's a really clever way to look at the problem. And you want to know why this is so slick? Because by defining our currents this way, as these little loops, we automatically satisfy Kirchhoff's current law everywhere. It's baked right into the method. That just saved us a huge step, meaning we only have to worry about the voltage law now. Now, there is one little catch. This method really only works for what we call planar circuits, basically ones you can draw flat on a piece of paper without any wires crossing over each other. So, yeah, it's a specialized tool, but for the right kind of job, it is an absolute lifesaver. All right, get ready. It's time for the main event. This next technique, it's a true game changer. This isn't just about solving a complex circuit. It's about making the complexity itself just disappear. This right here is the incredible promise of Thevenin's and Norton's theorems. It means that no matter how ridiculously complicated a circuit looks, you can shrink the whole thing down to its absolute simplest form. I mean, just look at this transformation. On the left, you've got this tangled web of components. And on the right, that's its Thevenin equivalent. Just one single voltage source and one single resistor. And here's the crazy part. From the perspective of anything connected to those two terminals, they behave exactly the same. It's the ultimate black box trick. So how do you actually find it? Well, to get that Thevenin voltage, you literally just measure or calculate the voltage across the terminals when nothing is connected to them. That's it. It's the open circuit voltage. It's honestly that simple. And there's another version of this trick, the Norton equivalent. It's the same core idea, but you use a current source in parallel with a resistor instead. To find that Norton current, you just imagine a wire connecting the two terminals, a short circuit, and find the current that flows through it. Two different paths to the exact same simple answer. So, there you have it. In just a few minutes, we've gone from being totally stuck to being basically unstoppable. Let's take a quick look at the brand new, fully loaded circuit analysis toolbox we just built together. You now have the node voltage method for finding those key pressure points. You've got the mesh current method for tracing the flow in flat circuits. And you have the unbelievable power of Thevenin and Norton equivalents to simplify anything. You're pretty much ready for whatever a circuit diagram can throw at you. And why is all this so important? Because these tools are the foundation for even more advanced techniques, things like superposition or figuring out maximum power transfer. That last one is absolutely critical in designing things like radio transmitters and receivers. These are the concepts engineers use every single day. So the next time you're faced with a complicated circuit, don't get intimidated, don't back down. You now have the tools to analyze it, to simplify it, and to conquer it. The only question left is, what incredible problems are you going to solve with your new superpowers?